Hey everyone, in this video we're simply just going to cover some examples from the material that we looked at in light, refraction and thin lenses, part 1.
Okay, so here we have our first question. A spherical surface made from high index glass, a refractive index of 1.71, has a power of minus 40 diopters. Locate the secondary and the primary focal points. So, what do we have? We have our refractive index and we have the refractive power of the surface. So because of these two components here, we can use our formula, the refractive power of a surface. So we will have P, modulus of P, N prime over F prime. So we have the power of our refractive surface, which is minus 450. Then we have our refractive index of our surface, 1.71. This goes over secondary focal point. And now we just restructure the equation. We're going to have 1.71 over minus 450 modulus. Our F prime is still over here. And using our calculator, 1.71 over minus 450 gives us minus 0.38, but again it's modulus, so it's a 0.38. That will be in meters, or we can say 38 centimeters. That handwriting though. So we have our primary focal point, which is equal to N over F. And when we restructure this one time, we're going to get focal point is equal to our P, which is minus 450. And over that, we're going to have our refractive index of 1, modulus of that. We plug this into our calculator. 1 divided by minus 450. We're going to get 0.0 0.222. That will be meters, or you can say 22.2 centimeters. And also, if we wanted to, we could plug in these values here now. So our secondary focal point, or focal length from here to about approximately here, is 38 centimeters, and then our primary focal length from here to here is 22.2 centimeters. And now moving on to our next question, we have a +4 spherical high index glass, 1.71 refractive index. It sits 66.67 centimeters away from an object that is 4 centimeters high. What is the difference, or rather, what is the distance between the image and the apex of the lens? So between the image and the apex of the lens, is it a real image, or is it virtual? Is it erect, or is it inverted? And what is the height? So let's look at what we have. We have the refractive index, we have the power of the surface, we have the focal length, and the secondary focal length, and we also have the height of the image. So let's start with the object vergence. So we have L is equal to N on L. We're going to find the vergence here. So we have N, which is 1, and then we have the focal length, or the distance of the object to the surface, the principal plane there, 66.67 centimeters. So we're going to put this in meters under here, so it will be 0.6667, and let's see what we get using our calculator. 1 divided by 0.6667, and we're going to get minus 150, approximately minus 150 diopters. Now using this, we can then use our Virgins relationship equation, which is L prime is equal to P plus L, or the image. So in this case, L prime is going to be equal to the plus 4 of our surface, and the Virgins that we have found, minus 150. Simple maths, we have plus 250 diopters of image Virgins. So object Virgins minus 150, image Virgin 250. So we can actually place this here, 250 image Virgins minus 150 object Virgins. Now using the image Virgins, we can find the image distance using similar formula, n prime over L prime. So we have our 1.71 over L prime. Rearranging the equation, we're going to get L prime is equal to 1.71 over our image Virgins, which is our plus 250. And what do we get when we plug this into our calculator? 1.71 over plus 250, we will get 0.684. So 0.684 meters, or again in centimeters, 68.4 centimeters. So what we found, we have the distance between the image and the apex of the lens. That's our first step. Is the image real or is it virtual? And we can tell this simply by our plus 250. This means that it's a converging system, and therefore our image is real. Is it erect or inverted? Or what is the height of the image? To calculate that, we would need to calculate the magnification. So how do we calculate magnification? Our magnification is M L over L prime. What is L? Minus 150. What is L prime? Plus 250, as we have indicated here. Now what do we get when we plug this into our calculator? Minus 150 over plus 250, and we get approximately minus 0.6 magnification. However, we still need what is the height of the image. The height of the image is simply the magnification times the object size. So, as I said, magnification times the object size. You leave it, you don't need to change it into meter. Multiply them both, minus 0.6 multiplied by 4 is minus 2.4 centimeters. So as we can see, the image, is it erect or inverted? We have a minus here. Minus magnification indicates that it is inverted. Our height is minus 2.4. As we can see, it is minified compared to the object. So we can actually draw this. Let me try to draw this in. So we have a distance of 68. So we can go a little further down on this side, come up on this side. Our image will be formed here, and the image is inverted, and this distance, as I said, from what we calculated here, 68.4. Our height is 2.4 0.4. It's inverted, so minus. And there we have it for the second question. So now moving on to the third question. A plus 350 diopter thin lens is separated by 25 centimeters from another minus 150 diopter thin lens. A object 7 centimeters high is situated 48 centimeters in front of the first lens. So 48 centimeters away, we have another object 7 centimeters high. Locate the final image, calculate its size, and whether it is real, virtual, erect, or inverted. So again, using, what do we have? We have the power of the first lens, power of the second lens, the distance between them, and we have the object distance from the first lens. So let us find our object vergence. We have L over N, L. And remember, these are thin lenses, so we are not using the medium, the refractive index of the mediums. We are going to use the refractive index of the area around them, which is 1 A. And then we have the length of the object to the first thin lens, which is in meters will be 0.48. 0.48. And what do we get when we plug that into the calculator? We are going to get approximately minus 2 diopters. So now from that yet we can simply find our image vergence using our vergence relationship. So we have L, which is minus 2. We have the power of the first lens, which is plus 350. This will give us our L prime. And here we have plus 350 minus 2, that's plus 150 diopters. And through this we can find our object, or sorry, our image distance, N over L prime. So again, rearranging, we will get 1 over L prime, which is plus 150, 1 over 150, 0.667 meters, or 66.6, sorry, 66.7 centimeters. But as we can see from here, our image distance is larger, our image distance for the first lens is larger than the gap between both lenses. Therefore, before the image can be formed 66.7 centimeters away, it will pass through and be refracted by this lens. And this is what we call a virtual object. So what will be created is called a virtual object. And we'll need to calculate the vergence of this virtual object so we can use it as the new object to pass through our second lens. So now to find out the vergence for this new virtual object, we need to minus the 25 centimeters from 66.7 to find out to lead to find out the vergence of the new object or the virtual object. So we will have 66.7 minus 25, which will give us, using the calculator again, 41.7 centimeters. So now we can use this in our formula to find out the new vergence for our new or virtual object. 1 over 41.7. This will now give us 1 over 41.7 sorry, that would be 1 over 0.41, because we have to change this into, this needs to be changed into meters, 0.417. And that will give us now plus 239. And now from that, we have to find our new image distance. And our new image distance is simply the image formed when the vergence of this, our new object, passes through our minus 150 length. So as we know, we can use our vergence relationship as we did up here, L prime. Sorry about that. So L prime is equal to L plus P. So we have our L, which is plus 239. Our new P is, our P is minus 150 diopters. What do we get? Plus 2.39, and we minus our 150 from that. We're going to get 0.89 plus 0.89 diopters. Again, this is our new image vergence. So now our image vergence, we can use our new image vergence to calculate our image distance. So we're going to have to rearrange our formula again. We're going to have 1 over plus 0.89. And let's see what we get for that on our calculator. We're going to have plus 1.12 meters, or 112 centimeters. Also, just to backtrack a little bit from this, as we have seen our object vergence come through our lens and it is still a plus, this indicates that the object will be real because the vergence is still plus. So it's a convergent system it came through. Although it was minus, it still came out to be positive, or it still came out convergent. Although it went through that minus sense, came out convergent. So it's a real image. It's going to form a real image. So going back to the question, we had to locate the final image. We have found the final image. We had to calculate its size. So now we have to do that through a magnification calculation. So let's do that. So magnification, it's simply going to be the image formed by the first surface, the size of that image formed by the first surface, or plus 350 lens, the image it created, multiply by the image formed by the second surface, our minus 350 lens. So when we put all together, we have minus 2 over plus 150, multiply both again by the second image formed, plus 0.89. So let's double check, make sure those values are accurate. So minus 2 plus 150 plus 240, this should be 39 actually. And we're going to multiply out those using our calculator. So minus 2 over plus 150, make sure we have our brackets, multiplied by plus 2.39 over 0.89. And when we calculate both of them together, we're going to get minus 3.54. This minus indicates that our image is going to be inverted, and if we want to find the height of our image, we simply check back what is our image height, which is, let's see, in our question, 7 centimeters high. So we have 7 centimeters multiplied by our magnification, and that is going to give us 7 by minus 3.54 minus 2 24.78 centimeters. So that's the new height of our image form. So let's plug in the values that we got. So this image would have formed somewhere down the line here. So let's just draw that out. And the distance from the second thin lens to where the image formed will be 112 centimeters. Also, we had our virtual object was formed at what distance? 41.7 centimeters. So we could put some dash lines here. This is where the virtual object fell. 41.7 centimeters. We can also plug in our divergences. So our object divergence was -2 on this lens. For the second lens it was +239. Our image divergences go below. So our image divergence for the first was +150. And our image divergence for the second was +089. So we answered all the questions. The final image, 112 centimeters. Its size, -24.78 centimeters. Minus simply means that it is inverted, and it is real because our last image divergence was positive, meaning it was a convergent system. So we have a real image being formed. And that was our last question for this session we had on optics here. I really hope it helped in some form or manner. So once again, guys, thank you for watching this video on optics. I hope it helped. I really need the feedback on this video. Let me know how the articulation was. Let me know how the content was. I know the handwriting, we had a little on that a little bit, but all of that will develop. Don't forget to let me know how everything went. Let me know if you understand the content. I really hope you did. As I said, we will continue to build on this. We're going to go into accommodation. We're going to go into uncorrected refractive error in terms of optics in the coming videos. So once again, guys, hope you all enjoy the content. We're going to continue to see more. I'm out. Peace.